Okay, this is Dr. Clark again, and we're going to do another video doing an example from Chapter 7. So we're looking at a problem that involves matched pairs. So here's a problem from the book, The Effect of Oxytocin. The Reading the Mind and the Eyes test, or RMET, measures the ability of a person to infer the mental state of another from looking at facial expressions. Researchers conducted a study on the effect of oxytocin on people's performance on the RMET. 30 healthy male volunteers were administered oxytocin and a placebo, each as a nasal spray in a random order and with a week of washout period between the two treatments. 45 minutes after the administering of each treatment, participations were given the RMET. The researchers noted that the average increase in RMET score when on oxytocin compared to when on the placebo was 3 points, with a standard deviation of 7.54 points, and the differences in RMET scores are not strongly skewed. Okay, so that's the setup. We have this group of 30 males, aged 21 to 30. They take this test, and they take it twice with a week in between. One time they take it, they get the drug. One time they get a placebo. It's randomized which one they get first, and they don't know which one it is. So it's at least a blind test because they don't know. And then it turns out that if they compare their score with the placebo to the score with the oxytocin, or the oxytocin, that the score was 3 points higher on average in the sample. And so they want us to answer some questions. So let's kind of take these in order. So define in words the appropriate parameters of interest in the study and give a symbol to them. Okay, so what are the parameters of interest? Well, we want to know what's the true average increase in RMET score in the population resulting from administering oxytocin compared to the placebo. And the symbol we would use is mu D. It's the average of the differences. Is there a difference in score when you have oxytocin versus the placebo? And we're looking, to see if it's an increase from oxytocin versus the placebo. So we're subtracting the score with the oxytocin minus the score with the placebo. And it turns out in the sample, we did observe a difference. The population here, well, if you think about it, we've got 21 to 30-year-old healthy males. We don't know anything more than that other than they're volunteers. So maybe the population of interest is healthy males aged 21 to 30. And the next question says, use the symbols to state the null and alternative hypothesis. So if there is no connection between the oxytocin and the placebo and how well they do on the RMET test, then on average, the difference in those two scores should be 0. If there is something going on, then we would expect on average the difference in those two scores to not be 0. And that's what we're testing. What are the validity conditions? So if you recall, a matched pairs test is basically a one mean test because you're going to look at the mean of the differences. So even though you've got two sets of data, one for this drug and one for this one, you end up subtracting this one minus this one, this one minus this one, so you get just one column. And so what are the validity conditions for a one mean test? Well, you need to have at least 20 in the sample size, and here we have 30, so that's good. And also you don't want to have a strong skew in your data set. So that means that the differences shouldn't be strongly skewed, and it said that they weren't, so both validity conditions are met in this case. Then they want us to do a theory-based test and test the hypotheses. Okay, so what would a theory-based test look like? Well, we'd have to go to the applet. So if we go to the theory-based applet, so theory-based inference, for a matched pairs test, remember, it's really just a one mean test. So when you go to theory-based, you're just going to click the one mean option. And we had 30 in our sample. We had the mean in our sample was 3, and the standard deviation in our sample was 7.54. They didn't give us the data set here. If we had had the data set, we could have pasted it in, but we didn't have that. Also, if they'd given us the data set, we could have used the matched pairs applet. And that would have allowed us to see, you know, the oxytocin scores and the placebo scores and then subtract them and see what the differences are. But effectively, remember, once you've got the differences, you're doing a one mean test on the differences. So if we had the data, we could have done a simulation-based test using the matched pairs applet, but we didn't have that, so we're just basically pretending like we've got this set of data and it has a mean and a standard deviation, and we just took those things and plugged them in here. Okay, so how do you do a test? Well, we click on test, we calculate the p-value, the mu of the differences is 0, the mu of the differences isn't 0, and we get a t-statistic of 2.18 and a p-value of 0.0376. So because this is less than 0.05, I would say we've got at least strong evidence that this true mean of the differences is not 0. Okay, of course the sample mean wasn't 0, but the question is this far enough away from 0 to give us evidence that it's not plausible that this could be 0? And that's what we've seen here. So the t-statistic is 2.18, the p-value is 0.0376. Because that's less than 0.05, we have strong evidence that the average increase in RMET score from taking oxytocin is not 0. Okay, so it's not 0. What is it? That's going to be the next question here. You know, find a 95% confidence interval. So this is significance, this will be estimation. And so when we do the confidence interval, you can get that from the applet. Actually, we can just click confidence interval and it will give us a 95% confidence interval. And that turns out to be 0.1845 to 5.8155. So this means that we are 95% confident that on average, people in the population of interest will increase their RMET score by something between 0.1845 and 0.58155 points. So again, we don't know what the true mean for the population is. We're fairly confident it's not 0. We don't know what it is, but if we had to estimate it, we'd say it's somewhere between 0.18 and 5.8, right? And the idea is that you're going to increase, the score will increase after taking the oxytocin. All right, so that answers number F, and then the last question is provide a full 4-part conclusion, including comments on significance, estimation, causation, generalization. So kind of take what we've already talked about here, put it into one nice paragraph. So because the p-value was small, less than 0.05, we could even say, we concluded that we had significant evidence that mu d, the average difference in RMET score after taking oxytocin, was not 0. If it wasn't 0, what was it? Well, we estimate with 95% confidence that the true value of the parameter is between 0.18 and 5.8 points higher after taking oxytocin compared to placebo. True value of the parameter is the average difference in RMET score, so we could have said that there as well. Because this is a randomized experiment, we can infer that the change in RMET score is caused by the oxytocin, right? So they did a randomized experiment, they took 2 measurements, they flipped a coin as to which one they did first, the placebo or the oxytocin, and so the difference in scores can only be attributed to the presence of the oxytocin in one case and not in the other. And they did, I mean, good study design, they did a week in between so that any, that drug would get washed out of the system, etc. And since they randomized when they took one, if for some random reason people were sadder or worse one week than the other or whatever, it would have got kind of averaged out between which one got got the drug on one week and not on the other week. However, there is little information about the volunteers. We know they're all 21 to 30-year-old males, but even to generalize to that population would be risky without knowing more about how representative the volunteers are of that group. So maybe we could generalize to 21 to 30-year-old males, but it's a little risky without knowing a little bit more. All right, and then just a follow-up question here, the next one has us do some of these calculations by hand. So how would you compute the t-statistic and the confidence interval by hand if you didn't have the applet. Well, they gave us the average, the sample mean, and they gave us the sample standard deviation and the sample size, so we can compute the the t-statistic by hand. So remember the standard deviation of the null distribution. When we do a theory-based test, the question is how wide is this? We know it's going to be bell curve, but how wide is that bell curve going to be? Well, the standard deviation of the null distribution should be the sample standard deviation divided by the square root of the sample size. And so if the sample size is 30, square root of 30 is 5.48, sample standard deviation is 7.54, and so we'd expect the standard deviation of the null distribution to be 1.38, which is kind of what you're seeing here. This about 1.38 is the standard deviation. Oh, yep, exactly what we got there. And so the t-statistic measures how many standard deviations away in the null distribution is what your statistic was. Well, our observed statistic was 3, and the standard deviation is 1.38. So how many 1.38s is a 3? Well, it's 2.17 if you divide it, and that's your t-statistic. You can make the confidence interval by using the standard formula, statistic plus or minus multiplier times the standard deviation of the null distribution. If you have the null distribution, like here, you can see the standard deviation is 1.37, but we could use the formula to calculate it. And if you do that, you get 0.24 to 5.76, which is, I think, pretty similar to what we had before. Maybe not exactly the same. Maybe the computer is probably using 1.96 instead of 2 as the multiplier. That's technically the correct one, but 2 is fine. All right, so you can actually do the calculation by hand, and this is the same as what we did before for a one mean test, right? That's really what we're doing here. It's just the one mean is about differences. Okay, so that's a matched pairs problem. It's a nice kind of problem. Gives you a setup, asks you some questions, thinking about what's the design of the study and how does the statistics work out.